Before we dive in, it's important to be careful with our language when talking about the Big Bang. The Big Bang is often misunderstood. If we define it precisely as the moment when the universe was extremely hot and incredibly dense, then we're on safe ground. This is because we have observational evidence to back this up. We can look out into the sky and observe the cosmic microwave background radiation, which is the leftover heat from that early hot dense state. This radiation fills all space and gives us a snapshot of the universe when it was just about 380,000 years old. Our best current theory tells us that there was something before this hot, dense phase. This earlier time is known as the period of inflation. It's a fascinating idea that changes how we think about the universe's beginning. You might ask, what existed before the Big Bang? This question has puzzled scientists for a long time. For many years, it was considered impossible to answer. But recent developments have brought us closer to an explanation. Brian Cox, a famous physicist, revealed that the state before the Big Bang was actually terrifying. This is because it was very different from anything we usually imagine. Instead of being filled with matter and energy as we know it, the universe was cold, empty, and expanding extremely fast. During this phase, the universe expanded so rapidly that it stretched out space itself. This is the essence of cosmic inflation. The expansion eventually slowed down and stopped in certain regions. When the expansion stopped, the energy that had been driving it was suddenly released into space. This energy heated the universe up, creating all the particles that would form everything we see today: stars, planets, galaxies, and us. This event is what we call the Big Bang. But the Big Bang itself is not the very beginning, it's the start of the universe as we recognize it, full of hot particles and radiation. Scientists are still trying to understand what came before this moment, and it's a deep mystery that challenges our imagination. One exciting idea that has emerged is called eternal inflation. This is an extension of the inflation concept, suggesting that inflation never fully ends. Instead, it keeps going forever in some regions of space. Imagine the fabric of the universe, called space-time, being stretched like a giant rubber sheet. In some places, the stretching slows down, stopping inflation and creating what we call a bubble universe. Each of these bubbles undergoes its own Big Bang, forming a separate universe. Our own universe is just one of these bubbles. This idea leads to a mind-blowing picture. An infinite fractal multiverse, where countless Big Bangs happen forever, each creating its own universe with potentially different properties. This inflationary multiverse theory suggests that the cosmos is far more vast and complex than we ever imagined. In such a scenario, the idea of absolute nothingness becomes difficult to grasp. Even if all matter and energy were removed, the universe would not be truly empty. Our universe is full of many components: matter, radiation, antimatter, neutrinos, dark matter, and dark energy. These all exist and interact in different ways, filling the cosmos. Even if you somehow removed all energy, quantum fields would still exist. These fields are fundamental aspects of reality that cannot simply disappear. They cause a background energy called zero-point energy, a minimum amount of energy present even in empty space. This zero-point energy is the closest we can get to nothing inside our universe, but it still isn't truly nothing. It's a kind of something that always remains. Scientists have never been able to create or observe true absolute emptiness, a space with no energy, no particles, and no physical laws. Such a condition may be impossible within our universe, meaning that something always exists, even when it seems empty. So, when we ask if the universe came from nothing, science tells us the answer is complicated. Something always persists, whether particles, energy, or fields. Even if we removed all particles like photons or neutrinos, quantum fluctuations in empty space would still occur. The vacuum of space is not a simple void but a dynamic environment filled with fluctuating energy. If you move far away from any matter or energy sources and clear the area of electromagnetic or gravitational fields, you get the best approximation of emptiness. But even this space is filled with fundamental constants and laws of physics, and a persistent quantum field energy. This situation reflects a universe that never truly reaches zero energy or complete emptiness. As the universe expands, light stretches to longer wavelengths, lowering its energy and temperature. This process means the universe was much hotter in the past and is gradually cooling over time. The cosmic expansion also causes distances between objects in space to increase, making the universe larger every moment. If you imagine rewinding time back toward the Big Bang, the universe becomes smaller, denser, and hotter. Eventually, you reach a point called a singularity, where the laws of physics as we know them break down and quantities like density become infinite. The cyclic universe theory challenges the idea of a single beginning, suggesting that the universe might expand and contract repeatedly in cycles. But the traditional Big Bang theory has shaped much of our understanding of the cosmos. It predicts that the universe should be expanding, which we observe through the redshift of galaxies moving away from us. Early in the universe, matter and radiation were spread uniformly. Over time, gravity pulled matter together to form stars, galaxies, and clusters. Because the universe was so hot early on, stable atoms could not form, leading to a soup of particles and radiation. As the universe cooled, atoms formed, and the cosmic microwave background radiation was released, a faint glow we can still observe today. The Big Bang theory also predicts the existence of light elements like hydrogen, helium, and lithium, created during the universe's first few minutes. The theory has been supported by many observations and experiments, making it the most accepted explanation for the universe's origins. However, it also left some big puzzles unsolved. One is the horizon problem. Why is the universe so uniform in temperature across regions that couldn't have exchanged information or energy? Another is the flatness problem. Why does the universe appear spatially flat, with a perfect balance between expansion and gravity? Finally, the monopole problem. Why don't we observe exotic particles predicted by physics at high energies, like magnetic monopoles? These problems motivated the search for new ideas, leading to the development of cosmic inflation by Alan Guth in 1980. Inflation proposes a brief period of extremely rapid expansion before the hot Big Bang. During this time, the universe's energy was not in particles but stored in the fabric of space itself. This expansion stretched space enormously, solving the horizon and flatness problems by smoothing out the universe. It also explains why monopoles and other exotic particles are so rare. Inflation diluted their density to near zero. Inflation theory made predictions about tiny fluctuations in the density of matter in the early universe. These small irregularities eventually grew into galaxies and cosmic structures we see today. Observations of the cosmic microwave background confirm these predictions with remarkable precision. These tiny variations are nearly scale invariant and adiabatic, meaning they are consistent across scales and have no entropy change. They also appear on scales larger than light could have traveled since the Big Bang, supporting the inflation model. Inflation thus provides a powerful framework explaining the early universe and its evolution. Yet, some questions remain. Where did inflation itself begin? What caused the initial conditions for inflation? Is there a true beginning, or did the universe exist forever in some form? Scientists continue to investigate these mysteries, pushing the boundaries of knowledge. The interplay of quantum physics and cosmology opens exciting possibilities about the nature of reality. It may be that our universe is just one bubble in a vast multiverse, constantly forming and evolving. This journey to understand what happened before, during, and after the Big Bang continues to inspire scientists and curious minds alike. Subscribe to our channel and thanks for watching.